Right, so my name is Lew Yan Voon. I'm the dean of the college, but I'm also a physicist by training. I teach physics 1 and 2 here. My research is in quantum physics, nanomaterials, we call them, and you'll see why we use that term nano in a few minutes. And so I've been doing this for many years, and I will admit that I'm not an expert in sort of quantum computing, which is a term that a lot of people have heard and which we're going to talk about today. But again, having, doing research and teaching quantum over the years, at least that part I have in control, all right? So, well, again, so good evening, everybody. Glad you're all here. And let's see, I think I had already asked, there are some of you who have taken physics 1 and 2, some of you in chemistry and so on, and in computer science. Now, I will say that we will have a couple of equations on the slides. Now, there's not going to be a test, all right? So, but again, if you've taken physics, math, computer science, chemistry, whatever, you've seen some equations, so shouldn't be scared about them, okay? But there are going to be about 30 slides, so we'll probably take about 15 minutes to go through those. I'm going to try to do those in 45 minutes, but it might take a few more minutes. I hope that you can at least remember 1 or 2 slides, okay? Again, if you don't like equations, you can just close your eyes and, all right, and you can gloss over them, all right? Well, let's see. All right, so let me get started with some of the basic stuff about why we're doing this this evening. All right, so basically goes by the title there. It says 2025 International Year of Quantum Science and Technology. And so basically the United Nations every year would designate in that given year some theme to be the International Year of that, all right? And for this year, they chose 3 themes listed on the slide. And one of those, so I'm only going to talk about one of those, is quantum science and technology. Okay? And we'll see near the end why they chose this year to be the International Year of Quantum Science and Technology, all right? But they do this every year in order to increase awareness of those topics, all right? And again, so that's the reason I'm doing this. Basically, every university that has a science program, a physics program in the country is doing an event, an activity to celebrate this International Year of Quantum Science and Technology. So this is our UF celebration of the International Year of Quantum Science and Technology. Well, as I was saying, I'm going to have about 30 slides, going to cover a whole bunch of topics, a little bit about history, mostly about the science, the technology, and sort of applications in the real world today, all right? Let me just start by explaining, again, what is this thing that we call quantum? How does that fit in? Especially, again, if you've had a physics class, or you might be in physics 1, right? Or you had it. Well, in physics 1, you study what we call classical mechanics, right? The motion of objects that we can see with the naked eye, all right? So that could be cars moving, airplanes. It could even be the moon going around the Earth, all right? So all of these can be described by classical mechanics. And again, that's what you study in physics 1. Well, of course, there are things that unfortunately physics 1 cannot explain or cannot cover. One example would be when those things are actually moving very fast, right? They can be the same objects, those cars, but moving very fast. And what do we mean by fast? Some of you might already know, the fastest any object can move in the universe is the speed of light, right? That's a very high speed. If you're going at the speed of light, there's an example there. So for example, you can go, in 1 second, you would go around the Earth 7 times if you're going at that speed, all right? Well, again, so the physics you're learning in your physics 1 doesn't apply to those motion, all right? For that, we would need a different kind of theory, which is known as the theory of special relativity, and that was developed by Albert Einstein, and some of you again might know about that. Out of that theory came the famous equation E equals to mc squared, if you've heard, right? Have you heard of E equals to mc squared? Yeah, so that came out of it. But a real practical application of the theory of relativity is the fact that the GPS that we have that governs, the location using our cell phone, for example, would not be as precise as it is today if you do not incorporate that theory into developing that technology, right? So it's actually very real, the theory of special relativity. Of course, it's got a lot of weird things about it if you've heard, but that's not today's talk. Today is about the other regime that classical mechanics doesn't address, which is not the very fast speed, but the very small objects. You know, because again, I said classical mechanics, things you can see with your naked eyes. Well, how small would they be? They would be in the regime of what we call nanometers, so meters, and then you put the prefix nano, which is 10 to the minus 9, if you understand the scientific notation. If you want to get an idea of what that means, it's basically the dimensions of molecules, atoms, or in that picture, it's a DNA molecule, all right? So that's how small you have to be in order to kind of be able to really measure the effect of, or to show that the classical mechanics you're studying in Physics 1 doesn't really work well, right? Now, it turns out that there are actually many applications where, again, quantum is important. How many of you have a QLED TV? Have you heard of QLED? A couple of you. Actually, I don't have one. I should, right? Because the Q stands for quantum. All right? LED, I think everybody knows what an LED kind of, right? All light bulbs are LEDs today, I think. Well, you put the Q in front, it means you have very small particles inside your TV on the screen. And that's the reason why you have such a great resolution. All right? So that's one application of quantum. Well, let's see where that word came from. According to the Oxford Dictionary, apparently it came from Latin, quantus, and it was actually used in English apparently back in the 16th century, all right? And it stands for basically quantity, but it didn't come into physics until the 1900s. Now, before I actually explain what is quantum, let's look at some of the strange features, because actually that's kind of like the more interesting popular side to quantum mechanics, all right, or quantum theory. Let me start by one example that's so more scientific. Again, if you study chemistry, for example, or physics. Well, again, throughout this talk, I'll make a lot of reference again back to the classical mechanics that we're more familiar with. So in classical mechanics, for example, you might study satellite orbits or planetary systems, right? Well, satellites, we probably know, they don't last forever up in the sky, okay? Unfortunately, eventually they'll fall back down to Earth because they lose energy, all right? Well, when people were studying atoms, they tried to, again, they were developing this, so because remember, atoms are these small things, so they had to come up with a new theory because the electrons, so the atomic structure, I'm assuming most of you have heard about atomic structure, but basically you've got a nucleus, a central core, and then you've got electrons going around that central core, right? Again, similar to a planetary system, all right? Well, those electrons never fall into the nucleus, all right? If they did, we wouldn't be here today, all right? Matter would just vanish, all right? Why? Actually, nobody really knows why. By the way, physics doesn't really tell you exactly why. It provides a framework to understand or to predict some of the consequences of what we observe, right? So we observe that the electrons do not fall into the nucleus. Using the theory of quantum mechanics, we can actually predict other properties that we can then observe, right? So that's one difference between, again, the world of the small particles and the classical world, all right? The structure of atoms. Another example, I actually debated on having this one, but we're going to talk about quantum computing, and atoms are actually one of the major components of many of the quantum computers we have today. So I'm going to use this example. And again, starting with classical mechanics, well, we know the Earth rotates, spins about its own axis, right? Well, when people were studying, again, atoms, and those were like chemists and all that, they found that there was some property that had two values in their measurements, all right? Well, they associate that with a rotation because in rotation, you have two types of rotations. Can anybody guess what those might be? Clockwise or counterclockwise? All right. Well, so because they found two answers, they say, well, it's some kind of rotation. Well, it turns out it's not a real physical rotation in what we call physical space. But they like the concept, so they kind of use that, but they call it a spin. But because it's not real rotation, we don't call it the two answers clockwise or counterclockwise. They decided to call them up and down. That's two answers, right? Or plus or minus, okay? But also, again, with that sort of up and down, it seems to match a vector or an arrow. And hopefully, again, many of you have heard of a vector. Even if you haven't, basically, it's some quantity, whether it's physical or mathematical, that has a direction and a magnitude, a length, all right? Well, the reason I want to mention this is because when people, and those were, the first ones were Stern and Gerlach using that tabletop apparatus, very simple. They tried to measure that rotation or spin of the atoms. And imagine, for example, you have somebody and you try to cast a shadow using a flashlight. Well, depending upon the angle of your flashlight, the shadow will have different lengths, right? On the wall, for example, on the ground. Well, they kind of tried to do that with the atom. Not a flashlight, but something similar. It's actually a magnetic field. They found out the shadow was the same length all the time. They still had two possible answers, up or down, but it was the same length. So again, it was not like a traditional kind of vector. And so again, that's why they call it a spin. Now, the reason I'm talking about this, because later on we're going to talk about other things that have those two values. In a computer, you have something that has two values, 0 and 1 for the computer scientists, all right? All right, now we're going to get really much into sort of the modern day interest in quantum, which has to do with quantum computers and quantum cryptography, all right? And I'm going to introduce that as something interesting with this theorem. It's called a no cloning theorem. The mathematics, I'm not going to show you the math, it's actually college algebra. It's not very difficult. But again, in classical world, you've got a test. You can make a perfect copy of that, right? Might not be perfect depending on your copy machine, but you can read it. That's a classical world. Well, if you use something that's quantum, and now you say, what is something that's quantum? Well, that atom I was talking about, okay? So remember, there are maybe sort of two kinds of atoms, depending on whether they are spins or up or down, all right? But you don't know which one it is, okay? So we say that it's an unknown state, all right? It's in an unknown state, you don't know. Well, that theorem says if you don't know, if you use something that's quantum and you don't know its state, all right, you can never make a perfect copy of it. All right? If you can't make a perfect copy, so can you see the connection to security and cryptography and all that? You cannot kind of hack this because you cannot make a copy of it. That's how it gets into quantum information science, all right? So again, that's a very important, that's a fundamental theorem in quantum information science. And again, I mentioned it's the basis of quantum cryptography. And now there are other sort of terms that we use to describe quantum information science, like quantum computers and so on. I'll say they're not synonymous. And again, we'll see a little bit of what the differences are. Instead of getting, again, into the science, I want to kind of pause on the technical side and talk about something very important that everybody should know about. All right, again, if there's one slide you're going to remember, it should be this one. We call sometime in the future the Q day. That's going to be when everybody's going to know your passwords and your social security and all that. All right, somebody, well, the whole world's going to be able to crack the security of the internet. I think the primary modality is the RSA encryption, and I think there are other modalities, but so that's a prediction. Now, you might say it might be way in the future. Well, again, we don't know exactly when, but some are predicting in maybe less than 10 years. All right. So that's a good reason for changing your passwords in less than 10 years. All right. But yeah, the whole of the internet framework, finance, business, whatever, is going to be a mess if that day arrives. And so people are predicting that that would arrive when we have this thing called quantum computers, and I'll talk about what they are near the end. Maybe even more, not shocking, but I guess we should expect that, right? Again, there are always bad actors somewhere when there's an opportunity. So apparently, obviously, there are some bad actors who are already collecting all your encrypted passwords or whatever they are. They can't figure out what they are, but when they lay their hands on one of these quantum computers, they'll be able to figure it out within seconds. All right? Now, the next slide is kind of technical. I'm not even going to go over that. But maybe for the computer science students here, all right, I think maybe in one of your courses you might have, or you're going to study things like key distribution. Well, again, everything that's in the sort of classical world, you just put the word quantum in front, and you're in that new domain, all right? So people are doing research into that, so how we can prevent these Q day from happening, all right? Or they're certainly teaching that in some classes. All right, so going back to, again, what makes it so quantum so puzzling and interesting, and this is, I think, the last one I have on that theme. This is actually probably the one I find most interesting, and a lot of people actually do, because it's about reality. It's about philosophical implications of what the quantum theory tells us. And like I said, I haven't really told you what it does really, except where it applies and so on. But one of the things that it does, it tells us that, again, if you remember, let's say your physics one, where you calculate, you have what we call the equations of motion, V final equals to V initial plus acceleration times time. Some of you who've had physics, hopefully you remember that. You know exactly where it's going to be, where that particle is going to be, or how fast it's going to be moving, if you know everything before exactly, all right? Well, quantum says you never, well, I shouldn't say never. There are some instances when you do, but in general, you do not know the answers exactly. You only know probabilities. So I can give you a probability for finding a particle or a car here, and a car over there, all right? And Einstein, who actually helped develop quantum mechanics, didn't like that version. He thinks the world is kind of real, and you have to know the answer for sure. You can't just live in a world of probability. So he was quoted as saying that apparently God doesn't play with dice, all right? That's not the way the world was created, right? There are some people who dispute whether that's what he actually meant and so on. So I copied the German original quote that I found online. If anybody speaks German or knows German, you can read that. But I think that's a pretty good translation. Some of the very strange things that you can kind of envision coming out of quantum theory would be something like teleportation, right? Again, I'm going to give a few examples. I won't have time to go through every one of them in detail, but teleportation, if you watch, for example, Star Trek, right? Beam me up, Scotty, and that kind of stuff. Well, it's not the same. So you cannot teletransport somebody, but you can teletransport what we call information, knowledge. Many-universe theory, I'll just describe that a little bit. Again, that's a sort of an interpretation of quantum mechanics. So if you look at the theory again, you study it, some people say, oh, what it's telling me is the following. So in quantum mechanics, an observation, a measurement, right, measuring the position of an object, and so on, is important. All right, it's an important act, it's an important event. And so some people said, okay, what the theory is telling me is the following. every time I observe something, so let's say I'm tossing a coin, right? Well, there are two possible answers, head or tail, all right? Well, and we'll see that in a little bit more sort of the mathematics shortly, but basically, one interpretation of quantum mechanics is the following, is that when you toss that coin, the universe breaks into two parallel universes. In one universe, you're there and you see a head. In the other universe, you're there seeing a tail. So both happen. So every time you sneeze, there are millions of mini universes being created and so on and so forth. Again, is that real? I don't know. But that comes out of quantum mechanics. Wave-particle duality, I understand some of you in physics too are actually studying waves right now. And again, I'm not going to go into the details, but basically quantum mechanics actually kind of says, well, we tend to think of, let's say, ourselves as being real material, right? Matter. Well, quantum mechanics says, well, maybe you're not matter, you're waves. Okay, like water waves, all right? And vice versa. The last one, I'm going to go into it a little bit, but it's the Schrodinger's cat. But to explain what that one is, I would now have to really get into the science of quantum mechanics. So this is where the equations are going to show up. All right? Well, again, I'm going to use a comparison to classical mechanics now. If you had physics 1, this is what we call classical mechanics, or some people call it Newtonian mechanics, because most of that was developed by Sir Isaac Newton on the right. And you guys remember Newton's laws of motion? How many of them are there? 3. And that one's the second one, right? Force equals to mass times acceleration, right? It's actually a very simple equation. F equals to ma, 3 letters, okay? That's the whole of classical mechanics that we teach you in 15 weeks. I know your physics professors will disagree, right? Or you will disagree. But that's pretty much all right? Those of you in the calculus sequence, we would use this form of that equation. This is calculus, differentiation. It looks a lot more complicated, but it's still just those 2 equations. Well, you ready for quantum? Physics 3, right? Who wants to take physics 3? Oops, where is it? Oh, I'm using the wrong computer. There we go. Not bad. It fits on a tablet, right? There are only 4 statements. The original tablet had 10, right? The first one is an equation. Don't worry too much what it means. I'm not going to describe what it means, right? But it's the replacement for the F equals to ma, okay? But it's short, right? It's not even a line. The second one is actually something I already talked about. I said, whenever you measure something, you don't get an exact answer. You get a property that you have an answer. Is that okay? There's no proof or whatever it is. That's why it's called a Born postulate, all right? We find out if we make that postulate, we assume that is the case, then we get the right answers, all right? The third one is the real mathematical one. Unfortunately, I can't skip it because that's the whole basis, again, of the quantum information science, all right? But let me try to kind of explain what is there. So it's called the principle of superposition. Again, if you've studied waves, then you probably learn about principle of superposition. Basically, it's saying that, again, that quantum state, okay? So yeah, if you say, what is a quantum state? Think about, I give you an atom of hydrogen, oxygen, whatever, and it can have maybe those 2 possible answers if you do some measurement. What are those 2 answers? Up or down, all right? Well, actually, quantum mechanics says no. You can also have the quantum state in what they call a linear combination. You can add those 2 together, all right? And another way to explain that might be kind of like a vector, okay? So if you have a vector in 3 dimensions, so if I say, what's the position here? You can say, okay, I can walk, like a few centimeters this way, right? That's one direction. Then you add a few centimeters that way and the third direction, all right? You're adding 3 sort of numbers, You're not reading numbers, all right? And that's what we're doing here. We're adding 2 or 3 or whatever. So again, if it's a coin that you're flipping, the 2 answers are head and tail. So quantum mechanics says, actually, in general, that coin is not going to be either just giving me a head or a tail, but it can give me a combination. Now, I know you say, well, what's a combination of a head and tail? That's the problem, okay? And we'll see that with the Schrodinger cat in a second. But the last one, so there's a 4th statement. It's known as the Copenhagen doctrine. And it says that when I make that observation, all right, that measurement, I get one of the answers that I should get. So yeah, if you toss that coin up while it's going up there and so on, you don't know whether it's a head or a tail that you're going to see, but when you look, you're going to see one of those 2 answers. You're not going to see half a head and half a tail, right, or something like that. So again, those are the 4 statements of fundamental statements of quantum mechanics. So you've already learned quantum by now, all right? So we need that to kind of understand this. So this was sort of a puzzle that this guy Schrodinger came up with to kind of, again, explain why, not really explain, to kind of illustrate how weird quantum mechanics is, okay? Because it is weird. There's linear combination. So he says, well, let's assume we have a cat. We should put into some black box with a radioactive material. Now, radioactive materials, they sort of decay randomly. You don't know when they're going to emit those radiations, right? So you don't know when the cat is going to get hit by the radiation and die and something like that. So you put the cat in the box, black box, you don't know, you don't look at it. Now, if you open the box, what will you see? You will see the cat either alive or dead, right? So that's the A, alive or dead, all right? But quantum mechanics says, no, before you look, it's in that unknown quantum state. It can be in a combination of alive and dead. Now, what's the combination of alive and dead? Halloween is coming. It's a zombie cat. Pre-vet students, don't put that on your test. Okay? So quantum mechanics says you could have a zombie cat. But when you look, you will get, so look is measurement, you'll see the cat either alive or dead. All right? That's the collapse of the quantum state. It collapses to one of the 2. Now, actually, Einstein didn't believe in this whole argument, by the way. So if you're saying, well, this doesn't make sense, you're not alone, right? All right, so that's the basic science, okay? Now I'm going to get into technology, right? The application. So technology basically refers to harnessing that science and doing something with it, all right? I mean, first of all, again, quantum is nothing that's not in this world. We are made of atoms. And remember, again, atoms are governed by the rules of quantum mechanics. So that's why I say everything is quantum. And if you're a chemistry major or you're taking chemistry, chemistry is all about quantum because you study atoms and molecules and all that kind of stuff. But again, that's sort of the science and the reality. And the technology, people tend to say that it started. So the theory came about in the 1900s or so, all right? And so it took about 50 years before we got something called the transistor. If you don't know what a transistor is, if you're an electrical engineer, you study transistors, but they are those things that are inside the chips, inside your computers or your cell phones. Okay, there are billions and billions and billions of those transistors inside your cell phones, right? So without, and the way they operate is based upon the laws of quantum mechanics because they're very small. You get that? All right. And so if we didn't have quantum mechanics, they would not have been able to develop transistors and you wouldn't have all these devices that you have today. All right. So that's the reason why they call that a quantum and the first quantum revolution and the information age. And this is probably just native to the US. In 2000, then president, who knows who was the president at the time? American history. Bill Clinton. He understood again the importance of harnessing this quantum, right? And instead of using the word quantum, they use the word nano. Why? Because again, remember, quantum is the small things, and small things are on the scale of nano. So they call it the nanotechnology, and put in billions and trillions of federal money into research in that area. And one reason I like to mention is because I just finished grad school, and I got a few pennies of those billions of dollars. It actually launched my career. And oops, again, wrong computer. Sorry. But today, we're looking at quantum information science as the next revolution, all right? And again, that's part of the reason why the United Nations as well decided to designate this year to be the year of quantum. I'll say very quickly, I mean, we've been doing quantum information science for actually probably a couple of decades, just like AI, all right? I did AI when I was in grad school, but my AI was very small, okay, like 10 data points. Today, the AI has billions and billions of data points, all right? So we've been doing quantum information science for many decades. The only problem is that we just haven't been able to harness the full potential because, again, remember what's a quantum state? It's like this atom that has those two properties, right? Or two values of that property. And if it's something very small, it's so easy to perturb it, right? To change it from one state to the other. I mean, just imagine again, you have a small ball, well, you know, a big object can just kick it from one location to another, right? So even temperature can easily change the nature of that quantum state. So they're not very stable, and that's the reason we don't have that revolution yet, all right? But again, to explain where we are a little bit in this technology, I'm going to use two examples, and I'm going to talk about quantum computers, but I like to start with encryption first because sometimes people think that, again, when you're talking about all this quantum information, you need to have a quantum computer. No, you don't, all right? So we can talk about this without having to talk about quantum computers, and then I'll explain what the computer is. So here's an example to illustrate what is quantum encryption. So let's say somebody has a secret message, all right? And so remember, now we're in the quantum regime, all right? So we can create a state of that atom or whatever it is as this linear combination, right? So again, like the alive and dead, right? So Alice actually created a zombie cat, okay? Of course, it's not a cat, so you can't do that with a cat, but you can do it with atoms, all right? And then if somebody else looks at, again, think about the cat in the box, right? Opens the box and looks at it. Again, they'll only see one of the two answers, right? Alive or dead, right? Well, what has happened? They've destroyed the original message or state. They are not seeing that first line, they're seeing the second line. So your message is secure. You see that? They only see A or D, they're not seeing that other equation in the previous line. So again, that's the basic principle behind using quantum states to have secure information, all right? Okay. So that's kind of a quick description of what quantum encryption stands for. Now I'll go into the sort of the last technical topic. What is a quantum computer? All right. Well, you take a classical computer. It's made up of what? Those chips, and the chips are made up of silicon atoms. Okay. Now but obviously a lot of them. For a quantum computer, we're going to use, well, most people actually today use atoms, but you can use other superconducting. I guess actually I forgot to put the next word, like superconducting circuits and so on. But basically, you can just think about the example of the atoms, right? So I've already explained why an atom can be this quantum object, because it has that spin property that's plus or minus or up and down, all right? And so let's see how that connects to a computer, classical computer. Well, I've already kind of given you that answer. A classical computer uses binary arithmetic, right? You have the zeros and the ones, and that's the information inside a classical computer. It manipulates these zeros and ones, right? We call those zeros and ones bits. And now, again, a physical computer, well, we need electricity, right? So the zero actually corresponds physically to, let's say, zero electricity or zero voltage. And the one corresponds to a high voltage of 5 volts, or approximately, all right? So that's how classical computers actually work. And by the way, again, if you have even a tablet or a laptop, one of the parameters to look for when you buy one of those is how much memory it has. And you probably want, if it's a laptop, with at least maybe 16 gigabyte to be able to run Windows efficiently, right? If you want to play games, you want probably 32 gigabyte at the very least, if not more. The giga is 10 to the 9. The byte is not bit, okay? So byte is B-Y-T-E. 1 byte is 8 bits, all right? Now, if you just write 0 and 1, they kind of get lost sometimes. So sometimes I like to put, like brackets surrounding them, all right? But we normally don't do that in classical computer science. Just to finish up, so that was 1 bit. And with 1 bit, you can only represent either a 0 or a 1. If you have 2 bits, so like 2 zeros, that's a number 0. If the 2 bits are, one is 0 and the other one is 1, it's 1, and so on. So you can represent numbers from 0 to 3. Okay, there are 4 combinations of 0 and 1s, the 2 of them, all right? So if you have a computer with only a memory with only 2 bits, you can think of them as 2 boxes, okay? You can only store 4 numbers in it, kind of, all right? So you couldn't even add 4 plus 4 or 3 plus 3, because that number 6 is going to be outside of your, you need more than 2 boxes to store a number 6, all right? So that's the reason why you want more memory, okay? For example, letters like A, it's not a number. So the way you can convert that into numbers in the computer is by giving it a code, a number. I don't know why. The computer scientists can tell me why. I never look it up, but they chose 65, and in binary, it's the number on the right. I'm sure your CS professors will double check my work. They'd make sure I did it correctly. Oops. All right, so that's a classical computer. What's a quantum computer, or what does it use? Again, it will be made up of all these atoms, all right? And these atoms can be a 0 or a 1, can be an up or a down. Is that okay? And so that's what you're going to kind of transfer the information. You move those atoms into those 2 possible states. So then they'll be doing something very similar to a classical computer. The one difference is, well, those are not the only 2 sort of states those atoms can be in. According to quantum mechanics, they can be into that combination state. So what happens here is that this is 1 bit, 1 storage box in a quantum computer. If you have this thing called a quantum computer, all right? This would be one of those boxes. Like up there, that's 1 box for a classical computer. But the 1 box in a quantum computer has the same amount of information as 2 boxes in your classical computer. You see that? Okay. I know you only need 1 box to put a 0 or a 1, but here we're going to have both a 0 and a 1. So you can't squeeze the 2 numbers into 1 box. So you need to have 2 boxes. So that's a way to describe how a quantum computer with just 1 box, 1 bit, a qubit we call it, has more sort of storage space than a classical computer, or has the equivalent one to a classical computer with 2 bits. This kind of representation of that the red arrow is set sort of that up or down thing in a computer. If it's up, it's a 0. If it's down, it's a 1. That's the choose. But the arrow can be anywhere in between, all right? All right, let's, oops, sorry. So let's see then how much more powerful can you make a quantum computer versus a classical one. So just to start again, if you have a classical computer with just one bit, you can represent either 0 or 1, but that's just one number, all right? Because you only do it once, okay? You can't do them both at the same time. If you have 2 bits, it's still one number. There are 4 possible choices of a number, but you're still having one number, all right? If we have a quantum computer, what I just said on the previous slide, if you have 1 qubit, you actually have 2 numbers. You have this number and that number in the classical computer, all right? 2 is the same as 2 to the power of 1, all right? If I have 2 qubits now, you don't have to worry about this math here. If you have 2 qubits, we would actually need to, it would correspond to 4 numbers. And 4 is 2 to the power of 2, all right? So what do you think would be if I have, let's say, 100 qubits? Anybody know how many on the other side it would match? See if I can close this. I'll pull up, I'm going to cheat. I'm going to pull up a calculator. Okay, so you do 2, oops, yeah, to the power of 100. Can you read this? Lots of digits, right? Well, the answer is if you have 100 boxes in your quantum computer, it matches a classical computer that would have 10 to the 20 gigabyte. Okay, that's 20 zeros. Remember, right now your computer only has maybe 32 gigabyte, okay? So that's what's showing that the quantum computer is going to be so much more powerful than the classical one. Here's one of those. If you think I'm just talking about things that don't exist, that's a quantum computer right there, all right? This is one made by this company, and it has 9 qubits. Actually, some people are saying there are computers out there with 100, with 1,000 qubits. Right? I didn't research. The reason I picked this one is because it has some nice pictures, and it has the price there. It's $3 million if you want to buy one of those. Christmas is close, right? Let's see. Look, you can go to their website and order yours. Look, credit card. Don't give that to your kids. You wouldn't like the bill. All right, but you can buy a quantum computer today for $3 million. They have a nice video of how you put one together.
The Novera QPU is here, a product of Rigetti's pioneering R&D. Far more than a chip. Save time, get to the important work now.
So that they are assembling, and you can see the size of it, right? That's the CPU basically, well, CPU plus all the wires that go with it, all right, of your quantum computer.
The Novera QPU is plug and play in your lab. Descended from Rigetti's most powerful systems.
Now this one doesn't use atoms, it uses those superconducting circuits. So it's sending electrical signals, and they're doing, those funny things. And then they put that, so here it is outside, and then they put that inside that white sort of enclosure or container, because they need to control the environment, the temperature, and that kind of stuff. All right. So that's an example of a quantum computer that's out there that you can buy. Again, there are many other ones. The second one, I just put this example there just to show where your people are using them. They use them for doing AI work. They're using it for material science. The banks are buying quantum computers to do some of their work, all right? And IBM, obviously, everybody knows IBM is a reputable company. They are, I think, a little bit behind the curve, but they're saying maybe in about 5 years, they'll come up with one that has a memory, that RAM of more than I don't even know what that word is, I didn't look it up. That's probably that 10 to the 20 gigabyte that I show you, something of very similar, right? Doesn't matter, 1 or 2 zeros difference. Okay, so last couple of slides, a little bit about history. So why did the United Nations choose this year? Because actually, probably the first paper on quantum started in 1900 by Max Planck. He used the word quantum, all right? So I think we can give that to him. And then there were other papers, like say Einstein worked on it and so on. But in 1925, so exactly 100 years ago, Heisenberg came up with new equations to replace Newton's law. Does that make sense? Or is something wrong here? What are those equations that replace Newton's law called? Schrodinger's equation, all right? Well, Heisenberg actually did it before Schrodinger, but most people are not using Heisenberg's equation. They're using the equations that Schrodinger came up with. So that's that. Oh, I guess I have a little bit about the financial landscape and the business landscape and so on. I think I'm going to skip. I have a link from MIT about showing the value of it, but so some of the studies have shown that this is a business that's about $1 billion and will grow to about maybe 7 billion in about 5 years' time. Let me skip that one. If you're looking for a job when you graduate, there are plenty of jobs. For example, they're predicting that in Colorado, there are about 3,000 in this quantum industry. They're going to need about 30,000 in 10 years. I don't know if the numbers for Chicago are right. It's like 400. I'm sure there are more than 400 jobs, almost 200,000 in 10 years. But also, according to that slide, again, you don't have to study physics, quantum physics, to work in the quantum industry. Of course, I'm a physicist, I would like you to get a degree in physics. But just like any industry, right? I mean, you need all the associated expertise, components, and so on, all right? So again, just the standard data scientists, computer scientists, engineers, and technicians and all that are going to be needed, making up all these 30,000 or 200,000 jobs at those places. Here's an example of an ad for one of those jobs that's a bit old, 3 years old, from Microsoft. We don't need to read the whole thing. I put in red some of the keywords. But again, basically you can take a standard software job today or engineering job today and put the word quantum in front, all right? So quantum language compilers, quantum engineer. But look at some of the experience you need or proficiency in Python. So if you're a CS major today, I hope you're learning Python. And basically my last slide here, so I think I said, well, we're in Ohio, so I need to say something about, well, we saw about Colorado and Chicago, what's going on in Ohio. Of course, again, any major university is doing research in quantum, and we are as well here at University of Findlay. If you've heard Intel's trying, we don't know if they'll ever succeed, but they're trying to build this plant that's going to cost, what is it? I think $50 billion to build right outside Columbus. And they call it the 14A plant. Now, 14A is not the address, all right? A stands for angstrom. And if you haven't heard of the angstrom, 1 angstrom is like a meter kind of thing. It's actually 0.1 nanometer, 1/10 of a nanometer. So when they call it the 14A plant, it actually stands for the 1.4 nanometer plant, meaning they're going to try to make those transistors that are that kind of like that small. All right. The current technology is 18A chips. All right. That's the latest from Intel. And apparently that's even kind of behind some of the competitors like NVIDIA and Taiwan Semiconductor. All right. But yeah, so again, that's what Intel is trying to do to catch up with everybody else and have that plant down there. So, but again, in conclusion, we already have the quantum revolution. Actually, just in the last couple of weeks, they announced the Nobel Prizes for this year. And for physics, they give it for 3 people who actually demonstrated that you can actually demonstrate quantum, not in that nanoscale, but on a simple electrical circuit that big on your hand. Okay, so some of the stuff that I was saying maybe is no longer quite true. I was saying you can't do it, or you can't see it at the big scale, right? It has to be very small. That's why they got the Nobel Prize and not me, right? All right, I think that's all the slides I have. Thanks for your attention. Are there questions?